Good evening, everyone. My name is Harshita, and I'm a PhD student from the University of Leeds. I'll be presenting on the use of artificial intelligence for analyzing structure health monitoring data from concrete structures. My co-contributors are Dr. Kai Yang, Dr. Duncan Bowman, Dr. Srijat Nanukutan, Professor Anthony Khan, and Professor Mohammad Bashir. Outline of the presentation, I'll discuss about structure health monitoring, its issues, role of artificial intelligence in structure health monitoring, research objectives, experimental details, initial observations from the data, application of AI to SHM data, results and conclusions and recommendations for future works. So let me begin my presentation by saying, if you can predict it, you can prevent it. So that is the rationale behind structure health monitoring. Structure health monitoring is an innovative technology that automatically sense, provide, and evaluate timely information about the condition and performance of structure at both global and local levels. So what it does is it uses sensors and sensing systems installed on the structures for monitoring. And data is collected via cloud computing on remote desktops, which is further analyzed, and it notifies if there is any faults in the structure for plan of action and maintenance procedure. So its advantages are increased serviceability, improved safety, and real-time maintenance. However, it has certain issues. That is, the current practice of collecting massive, uncertain sensor data is difficult to process. It's not easy to identify defects from the noise. And thirdly, the wrong judgment could trigger untimely maintenance and repairs, resulting in increased cost of maintenance. Therefore, the potential solution can be to apply AI-enhanced structure health monitoring methodology for data processing and decision-making for better in-service performance of structures. Application of AI in structure health monitoring. AI has been already used in structural health monitoring to enhance its building performance for early detection of deterioration of structures. It is used to identify, locate, and quantify defects, or to capture changes in natural vibration frequencies and mode shapes. However, it has not been used to extract reliable information of material properties from sensor data, and therefore to capture their changes for decision-making to predict the in-service performance of structures. Therefore, the objective of this research is to apply AI to SHM data that is obtained from electrical resistance sensors, and therefore demonstrate the advantages of using this method over manual data analysis for assessing the performance of concrete in service. In order to do that, we have collected data from an experimental case study where 3 high-performance concrete mixes with 2 samples of each mix were casted, including Portland cement, pulverized fuel ash, and microsilica. These blocks were cured for 3 days and then kept outside in an open area on the 4th day. These blocks were exposed 1 meter apart from a 3-story building in Belfast. These blocks were embedded with multi-electrode array for acquiring electrical measurements and thermistors for temperature measurements. They were kept at 3 different depths, 15 mm, 25 mm, and 45 mm depth. The data was recorded every 10 minutes for 6 months in the data logger, and we gathered over 24,000 sets of data in total. This raw data was then converted into useful and suitable format for analysis. At this point, we identified that there were some missing values, duplication of data or invalid data or noisy data, which was identified and then removed to reduce its influence. So as we know that the concrete is affected by the temperature. So if you see in the graph, the squared blocks represents as measured resistance, and there is huge diurnal variation in resistance for all concrete types. This is because concrete was kept outside and it was subjected to temperature variations. So what we did was we applied Arrhenius equation to remove the influence of temperature on electrical resistance. So the acquired values of activation energy from the relationship enabled resistance measurements to be standardized to 25 degrees Celsius. So these huge fluctuations that were seen in as measured resistance were slightly reduced in standardized resistance, which can be seen here with circular data shows the standardized resistance. So the initial observations from the standardized data were that resistance increased over a period of time in all three concrete types. That is because resistance increases with the pozzolanic reaction of the binder material. Also, microsilica increased at a faster rate than PFA and PC because addition of supplementary cementitious materials alters the pore structure due to the pozzolanic reactivity. Finally, this resistance at deeper concrete is lower than at the surface because surface is releasing more moisture while the deeper part is saturated, and evaporation of moisture leads to increase in resistance. So the performance of concrete can be assessed based on electrical resistance and chloride diffusivity that can be calculated from electrical resistance. So it is essential to consider three parameters of resistance for further analysis, that is initial rate of increase in resistance, value of stabilized resistance, and time taken to reach a stabilized resistance value. So shown here in the graph is standardized resistance of microsilica with time. So the graph shown here can be seen that it does not represent a linear equation. So we cannot use linear regression. So that is why, although we can see that it is divided into various pieces, so we have used piecewise linear regression for the analysis. This method is easy to understand. However, it was difficult to identify the ultimate breakpoint to find the initial rate of increase and the value of stabilized resistance. And this was also time consuming. That is why we used an automated approach to calculate, to determine change in resistance gradient and stabilized value. In order to do that, the first step was to use a Gaussian weighted moving average filter to smooth the noisy data. So the noisy data is compressed, keeping the original trend. The second step was to use an AI-based application similar to k-means clustering, which divides the total data into two segments and identifies the maximum slope difference from the data, and shows the, in the step 4, it shows the ultimate breakpoint, which depicts the stabilized value of resistance and time taken to stabilize that resistance value. The slope of segment 2 here shows that resistance is still increasing, but at a slower rate. So this approach is easy to understand, faster, reliable, and easily interpretable. So results from the analysis. So resistance values were calculated using AI-enhanced approach for all three concrete types at 3 different depths. So initial rate of, so microsilica increased at a faster rate, followed by PFA and PC. Time taken to stabilize, microsilica took more time to stabilize than PFA and PC. This is because of the addition of supplementary cementitious material. It altered the pore structure. Also, microsilica is a denser material, leading to extensive increase in the resistance. Finally, this value of stabilized resistance was used to determine diffusion coefficient using this relationship dE by d naught equals to rho by rho bulk, which can be further used to predict the service life. The obtained diffusion coefficient value shows the opposite trend to that of the resistance. Therefore, the conclusions derived from the analysis is that the challenge identified in handling, smoothing, and analyzing large data set manually demonstrated that there is a need to resort to artificial intelligence for data analysis. This proposed methodology is faster and more efficient than the conventional approach. Third, the data highlighted that there is an effect of temperature and depth effect on resistance measurements for different concrete mixes. Fourth, this also demonstrated that the benefit of using supplementary cementitious materials in improving the durability of concrete. Finally, this AI-enhanced SHM methodology represents a reliable, easy interpretable, and effective approach that can be used for different types of concrete and structures for monitoring and calculation of resistance and diffusion coefficient to predict the performance of concrete and structures. We have few recommendations for future works. That is, the resistance data used here is for 6 months. So it is recommended to use long-term data to assess the effect of exposure environment on durability of concrete using electrical resistance sensors. It is also recommended to use relative humidity sensors inside and outside the concrete, and temperature sensors outside the concrete, so that if there is any influence of ambient environmental conditions that can be measured and can be determined. Finally, this proposed methodology to smooth noisy data and extract reliable information from large amount of data may be repeated for other concrete types and exposure conditions. However, we need to see that the smoothing window would change depending on the noise or the type of analysis we are using. Thank you so much. Any questions? Are the sensors applicable for industry field or just the research lab? We have used these sensor data for both industry, for the field work as well as for the research work, and this is applicable on both the cases.
I actually have a question related to different type of SCMs. Since you mentioned you use silica film, and I assume PFA is the fly ash.
Yes.
So have you ever tried slag or like any other SCMs? Because it seems to be a different curve shape regarding different SCMs.
Yeah, we have only used 3 type of mixes in this case. But yeah, if we use any other slag or any other material, then it will show different curves.
So in that case, is your model now applicable to other type of SCMs like clay or metakaolin or slags?
They can be applicable. We need to see the effect of temperature on all these materials we use.
Okay. So you just didn't have the chance to try it yet, but it's applicable, right?
Yes.
Okay, thank you.
What about the cost of these sensors? We have not considered the cost as for now, but we'll see in the future.
In that case, thank you again, Harshita.